A decoded transmission from a visitor that has just entered our solar system confirms a chilling reality we've long feared. In the year 2025, NASA officials confirmed that the interstellar object designated 3Y Atlas is not just a passing comet, it is broadcasting a message. What it says could, honestly, redefine humanity's place in the cosmos forever. Let's explore this together. The impossible visitor. What if our third confirmed interstellar guest wasn't just wandering through space but navigating it? When astronomical networks like Pan-STARRS first detected 3Y Atlas in early 2025, it shattered every known classification. Unlike previous interstellar visitors, it was traveling at an unusually high interstellar velocity of 45 kilometers per second relative to our Sun, on a trajectory with a hyperbolic eccentricity of over 3.5. But it was its behavior that was truly impossible. It executed deliberate course corrections, moving with a precision that honestly defied any natural explanation. This wasn't a random rock. Its massive coma, a gas and dust cloud stretching 700,000 kilometers across, pulsed with a steady, repeating electromagnetic signal, unlike the chaotic outgassing of a comet like Hale-Bopp. The trajectory it took was impossibly efficient, using the gravitational wells of planets it passed as if it had a complete map of our system, a feat that takes our own probes years of calculation to achieve. The sheer energy required for these maneuvers, conducted without any visible propellant, suggests a technology that operates outside our known physics. As 3I Atlas carved a path through our asteroid belt with surgical accuracy, it became clear this wasn't an exploration, it felt like an arrival. When physics stopped making sense. There are fundamental laws that govern how objects move in space, but 3I Atlas seems to ignore them. Its trajectory showed a smoothness and efficiency that decades of astronomical observations say is impossible for a natural body. Scientists at NASA began using a term that honestly sent shockwaves through the community-piloted behavior. It executed a course correction amounting to a 15-meter-per-second delta V with no detectable outgassing, a feat that directly violates the Tsiolkovsky rocket equation for an object of its mass. Theoretical physicist Michio Kaku, when presented with the data, noted that the energy required for such a maneuver would be in the terawatt range, equivalent to the entire power output of humanity, sustained for several minutes. To a physicist, this is like watching a multi-ton boulder suddenly levitate and change direction in mid-air. The violation of this fundamental principle sparked frantic debates within institutions like the Jet Propulsion Laboratory, where teams ran millions of simulations and could find no natural model, not even an exotic outgassing of unseen material, to fit the observed data. This wasn't just an anomaly that stretched our theories, it was a direct contradiction of known physical laws. The object that defied reality. When NASA aimed the James Webb Space Telescope at 3Y Atlas, the data it sent back challenged our understanding of reality itself. The thermal readings were the first red flag. Instead of chaotic heat bursts, 3I Atlas showed a consistent thermal signature of 250 Kelvin, pulsing with a precision of microseconds. JWST's principal investigator for the observation, Dr. Jane Rigby, noted that the thermal stability was unnatural. Webb's spectrography then revealed hyper-reflective compounds that appeared artificial, a material with a near-perfect albedo of 0.98, reflecting 98% of all light, something not found in nature. But the most disturbing discovery was a faint electromagnetic pulse repeating every 147.13 seconds. It matched the signature of a real pulsar PSRB 1919+21, yet the object had no magnetic field capable of generating it. It seemed to be mimicking a signal, a form of cosmic camouflage. Webb's infrared analysis also found structural patterns resembling recursive geometric fractals, leading some to float the terrifying consciousness engine theory, comparing it to theoretical concepts like a Matryoshka brain, but on a smaller mobile scale. The combination of these impossible features in one object moves it from unusual to unequivocally artificial. Two visitors, one terrifying pattern. This wasn't the first time we'd been sent a strange message. The mystery of 3I Atlas deepened when researchers cross-referenced its electromagnetic signature with archived data from Oumuamua from 2017. They found the exact same 147-second frequency had been detected briefly in its tail. The difference was the signal strength. Oumuamua's signal was a whisper in the microjanskis barely above the noise floor, while 3I Atlas is broadcasting in the millijanskis, 1,000 times stronger. This really reframed everything. Harvard astronomer Avi Loeb's controversial theory that Oumuamua was an alien solar sail suddenly gained terrifying new ground. The statistical improbability of two interstellar objects separated by 8 years from different star systems, sharing such an unnatural signal is astronomical, suggesting they are part of a coordinated system. Oumuamua's brief weak signal now looks less like a random anomaly, and more like a handshake or ping to test for a response. Now 3I Atlas is answering with a full-blown data stream, implying the test was successful, and our civilization has reached a specific technological threshold. When space objects make calculated decisions. The moment we knew for sure we were being actively monitored was the moment it changed course. Just as scientists believed they had mapped its future trajectory, the Very Large Telescope in Chile recorded a subtle but unmistakable 0.05-degree inclination shift, an adjustment of 180 arc-seconds. This wasn't the random drift of a comet. The object veered off its projected arc, aligning with a new vector that brought it closer to Earth's orbital plane. To mission analysts like planetary scientist Dr. Sarah Seeger, the implication was clear: this was a conscious decision. The maneuver occurred just 72 hours after the James Webb Space Telescope began its focused spectroscopic analysis, a time frame confirmed by NASA's Deep Space Network that rules out coincidence. This inclination shift is an incredibly energy-intensive move, and the action wasn't just responsive, it was almost defiant, a clear message that said, "We see you watching us." The mood at the DSN's Goldstone complex as they tracked this impossible change in real time shifted from academic curiosity to profound alarm. Ancient mathematics from the stars. The signal wasn't just a pulse, it was a message written in the oldest language in the universe. Independent cryptographers analyzing the emissions discovered something extraordinary hidden within the narrow band, 0.1 Hz-wide signal. They found precise mathematical ratios, the golden ratio, Fibonacci sequences, and prime number spirals. This is exactly what scientists like the late Carl Sagan predicted an intelligent signal would contain. The signal wasn't just a simple prime sequence, it was encoding the Riemann zeta function, a deeply complex mathematical concept related to the distribution of prime numbers. Furthermore, the signal's modulation, using a complex form of phase shift keying, corresponded to the value of pi to over 1,000 decimal places, an unmistakable beacon of intelligence. Frank Drake, creator of the famous Drake equation, would have seen this as a direct attempt to communicate not just presence, but profound intelligence. This wasn't a simple hello, it was a comprehensive intelligence test, broadcasted across the solar system for anyone smart enough to listen. Organic chemistry from beyond the stars. It wasn't just a machine, it was carrying the very building blocks of life. James Webb's detailed spectroscopic analysis revealed its outer shell was coated in complex carbon molecules, and its NIRSpec instrument found evidence of adenine, one of the 4 nucleobases in DNA, via clear absorption lines between 260 and 280 nanometers. What was alarming was the purity and organization of these molecules. Unlike the chaotic racemic mixture of amino acids found in the Murchison meteorite, the compounds on 3Y Atlas showed a 99.7% levorotatory excess, a homochiral signature that is a smoking gun for biological or artificial synthesis. Astrobiologist Dr. Heather Graham at NASA's Goddard Space Flight Center found the conclusion both thrilling and, honestly, terrifying. The terrifying implication is that if this is a seed ship, its purpose might not be benevolent. It could be preparing the environment for a subsequent colonization effort. The presence of DNA components suggests a biology that might be eerily compatible, or dangerously competitive, with our own. When Earth responded to the cosmic visitor. We thought we were only observing a distant object, but it was already interacting with our planet. A classified high-altitude surveillance balloon over Antarctica detected an extraordinary event. A powerful 500-megawatt tight-beam microwave burst at 23.4 gigahertz, lasting about 1.2 seconds, originating from the Amundsen-Scott South Pole Station's vicinity. The signal's timing aligned perfectly with another angular shift in 3Y Atlas's trajectory. Moments after the burst, seismic stations recorded ultra-low frequency rumbles, registering a 1.2 on the Richter scale, but resonating at a perfect 0.0068 Hz, the exact inverse of the 147-second pulse. Dr. Francis Halzen, principal investigator of the IceCube Neutrino Observatory, later reported a statistically significant 3 sigma spike in TV-range neutrinos from the same location. The synchronization implies the Earth itself is part of a much larger ancient network that is now being activated, with a dormant relay station buried deep beneath the ice. The Asteroid Belt Death Run. Right now, 3I Atlas is navigating a cosmic minefield, and it's doing so with terrifying ease. Its current path takes it directly through the main asteroid belt, traversing the dense Kirkwood gaps at over 60 kilometers per second. Unlike most comets, which have highly inclined orbits, 3Y Atlas is cutting directly through the belt's core. Planetary defense expert Dr. Amy Mainzer, former principal investigator of the NEOWISE survey, noted that its 700,000-kilometer coma is interacting with millions of untracked objects. More astonishingly, minor course corrections have been observed, suggesting it's actively avoiding even meter-sized debris with impossible precision. This avoidance system must be processing the trajectories of over 1.5 million known objects in real time, a feat of computation that dwarfs anything on Earth. Its journey isn't a dangerous run so much as a demonstration of effortless superiority over a hazardous environment, adjusting its path by mere hundreds of kilometers to avoid potential impacts. Rewiring our solar system's neural network. This object isn't just passing by, it may be fundamentally changing the space around us. Data from NASA's Parker Solar Probe, led by scientists like Dr. Noor-e Rawafi, confirms the object is generating alpha waves in the solar wind, disturbances measuring several nanoteslas that can transfer energy over vast distances. Scientists at NOAA's Space Weather Prediction Center are concerned these disturbances could amplify the effects of the next coronal mass ejection, potentially increasing the resulting geomagnetic storm's KP index by 2 to 3 points, pushing it from a moderate to a severe event. The charged dust particles it's shedding are acting as charge carriers, creating a persistent conductive path between the object and the sun's magnetic field lines. It is essentially inserting itself as an active electrical component into our solar system's delicate circuitry. The long-term consequences for planetary magnetospheres, including the one that protects all life on Earth, are completely unknown and deeply concerning. The universe has sent us messengers, and we are only just beginning to learn their language. The mysteries of Oumuamua and other interstellar visitors remind us that we are part of a vast, interconnected cosmos filled with wonders we are yet to discover. The journey into the unknown continues. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the frontiers of science. Thank you for watching InnoVision Tech. Humanity's farthest messengers are about to fall silent, but a plan is already taking shape to send a successor. For nearly 50 years, the Voyager probes have been our eyes and ears in the void, but their 1970s technology is fading. Now scientists are designing a true interstellar explorer, a robotic probe built to fly faster, see clearer, and journey deeper into the cosmic ocean than ever before. This is the story of the mission to build Voyager's heir. Let's explore this together. The original Voyager achievement. Ever wonder how 2 probes from the 1970s became the greatest explorers in human history? The answer is a mix of brilliant engineering and perfect timing. Managed by the Jet Propulsion Laboratory, Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that happens only once every 175 years. This grand tour alignment allowed them to use gravity assists, slingshotting from one giant planet to the next. Under the guidance of scientists like the legendary project scientist Ed Stone, who served for 50 years, the discoveries were staggering. We saw active volcanoes spewing sulfur on Jupiter's moon Io, confirming 9 active eruptions and making it the most geologically active object in the solar system. We discovered the icy geysers of Neptune's moon Triton, a world so cold it spews nitrogen frost. These missions completely rewrote planetary science textbooks, all accomplished with custom-built computers that had just 69.63 kilobytes of memory, less than 1/millionth of a single photo taken by a modern smartphone. They transformed our view of the outer planets from fuzzy telescope images into a detailed family portrait, revealing worlds more dynamic and complex than anyone had ever imagined. It was a mission of firsts, providing the data that forms the foundation of modern planetary science. A journey into interstellar space. But their planetary tour was just the first act. Once their primary mission ended in 1989 after the Neptune flyby, the Voyagers just kept going, beginning the Voyager Interstellar mission. Powered by their radioisotope thermoelectric generators, they traveled onward toward the boundary of our solar system. That boundary is the heliopause, the edge of the vast magnetic bubble our sun creates called the heliosphere. In August 2012, Voyager 1 finally crossed that boundary at a distance of 121 astronomical units, or 11 billion miles from the sun. The moment was confirmed by Don Gurnett and his team at the University of Iowa when the Plasma Wave System instrument detected the vibration of dense interstellar plasma, a 40-fold increase in density that sounded like a sudden tone in the data. It was the sound of leaving home. Voyager 2, which took a different route past Uranus and Neptune, followed in November 2018, crossing at a different point in our solar bubble and giving us a second, crucial data point. Right now, Voyager 1 is over 15 billion miles away, hurtling along at 38,000 miles per hour. This was a monumental achievement, marking the first time a human-made object had physically entered the space between the stars, our first tangible step into the larger galaxy. Current limitations of the Voyagers. Here's the fundamental problem. The Voyagers are technological marvels, but they are also relics. They were designed for the powerful environments of planets, not the subtle nuances of interstellar space. Their magnetometers, for example, were built to measure the powerful magnetic fields of gas giants, not the faint, tenuous fields between the stars. Their cosmic ray subsystem can detect energetic particles, but it lacks the sophistication to distinguish between different heavy elements with the precision a modern instrument could, which is critical for understanding the origin of these rays. Furthermore, their power source, which uses heat from decaying plutonium-238, is fading. The initial 470 watts of power has dwindled, losing about 4 watts of electrical power each year. To conserve what little energy remains, engineers on the ground are in a constant race against time, making difficult choices about which instruments to sacrifice next. Their data trickles home to the Deep Space Network at a mere 160 bits per second, meaning it would take over a week to send a single low-resolution photo. The signal is now so faint, billions of times weaker than a watch battery, that it requires the world's most sensitive radio antennas just to hear it. The case for Voyager 3. This is where the idea for a successor, which many call Voyager 3, becomes more than just a dream. While Voyager 3 isn't an official NASA name, it perfectly captures the spirit of a next-generation mission. The actual, formal concept being studied at the Johns Hopkins Applied Physics Laboratory for NASA is called the Interstellar Probe. Led by scientists like Principal Investigator Dr. Elena Provornikova, this would be humanity's first spacecraft specifically designed to explore interstellar space. Its entire purpose would be to journey beyond the sun's influence, born from the questions the Voyagers raised but could not answer. The goal is to build a probe that could operate for a minimum of 50 years and travel at a target speed of over 95,000 miles per hour. This incredible velocity would allow it to reach the heliopause in about 15 years, a journey that took Voyager 1 over 35 years. The mission's target isn't just the edge of the heliosphere, but a destination of 1,000 astronomical units into the truly undisturbed local interstellar medium. This distance is crucial because it's far enough away to be free from the sun's lingering influence, allowing us to sample the pristine material of our galaxy for the first time. Advanced technology capabilities. So what kind of upgrade would a modern interstellar probe get? Let me explain. Compared to the Voyager's 1970s technology, a new probe would be a revolutionary leap. Instead of limited sensors, it would carry a suite of advanced instruments, a plasma spectrometer, energetic particle detectors, magnetometers, and a dust counter, all with at least 100 times the resolution of the Voyager's equipment. Power would come from a next-generation RTG, designed for longevity and providing enough power to run a full suite of instruments for a century. But the real game-changer would be its brain AI-powered autonomous systems. This would allow it to make its own decisions, acting like a true robotic field scientist. It could prioritize data, compressing less important information to save bandwidth for groundbreaking discoveries, and even react to unforeseen events without waiting for the 3-day round-trip communication with Earth. To achieve its speed, the mission would launch on the most powerful rocket available, like NASA's SLS Block 2, and perform a powered Jupiter gravity assist, using both Jupiter's gravity and an onboard engine to achieve velocities previously thought impossible for a long-duration science mission. The interstellar medium mystery. Why is this so critical? Because our entire solar system is hurtling through a cosmic ocean, and we barely know anything about the water. This ocean is the interstellar medium. Our sun's solar wind carves out the heliosphere, which shields us from about 75% of the most energetic galactic cosmic rays. This shield works because the solar wind's outward pressure physically pushes away this deadly radiation. But what is its true shape? For years we thought it was a comet-shaped teardrop. However, models by scientists like Merav Ofer now suggest it might be a sphere or even a deflated croissant. A key unresolved question is how the interstellar magnetic field drapes around our heliosphere, which is crucial for its structure and how it protects us. Our solar system is currently passing through what's known as the local interstellar cloud, a slightly denser region of gas and dust. An interstellar probe could tell us how this local weather directly impacts the shape and strength of our protective bubble. Understanding this interaction is fundamental to understanding our own cosmic environment. Scientific objectives and research goals. Let's get specific. What questions would a mission like the Interstellar probe finally answer? First, it would explore the unshocked interstellar medium, the pristine galactic material our sun is moving through. This means getting a baseline chemical inventory of our galactic neighborhood, the very stuff from which future stars and planets will form. Second, it would map the structure of our heliosphere in high definition, crossing key boundaries like the termination shock and heliosheath with far more advanced instruments. It would finally solve the mystery of its shape and reveal the physics of its interaction with the galaxy. Finally, the mission would journey to a target of 1,000 astronomical units from the Sun. As physicist Ralph McNutt from the APL team emphasizes, getting to this distance would allow us to look back and view our solar system as a complete astrosphere for the first time. From this vantage point, it could even detect the faint extragalactic background light without interference from dust in our solar system, opening a new window for cosmology and studying the universe's first light. It would be a multi-purpose observatory unlike any other. Practical applications for future missions. This isn't just about abstract science, it's about laying the groundwork for humanity's future in space. Let me explain. Any future attempts at sending probes to other star systems will require navigating the interstellar medium. An interstellar probe would act as a pathfinder, creating the first detailed atlas of the space just outside our solar system. It would quantify the radiation risks for future robotic or human missions, which would be impossible without the precise data this probe would gather. At speeds over 90,000 miles per hour, even a tiny grain of interstellar dust can strike with the kinetic energy of a rifle bullet. So the probe would map dust density to inform shielding design for future, even faster craft. Developing the technology to reliably communicate with a probe hundreds of AU away would push our deep space communication capabilities, benefiting all future missions. Furthermore, it would pioneer techniques for autonomous interstellar navigation, a requirement for any craft that travels so far from home that the sun becomes just another bright star. This is essential for concepts like breakthrough starshot, which would need this data to even begin planning. Cultural significance and golden record 2.0. What message would you send to represent all of humanity on a journey that will outlast everyone alive today? In 1977, Carl Sagan's committee assembled the Golden Records. An interstellar probe would carry on this legacy, but a Golden Record 2.0 wouldn't be a physical disc. John Lomberg, the artist who designed the original record's cover, has proposed a digital successor. This new archive could hold petabytes of data, the entire human genome, vast libraries of art and science, and perhaps even messages from the public. The new message would have to reflect our more globalized, digitally connected, and perhaps more self-aware civilization. The very act of creating it forces us to reflect on our collective identity and what we would want to say about ourselves to the cosmos. How do you represent humanity's flaws alongside its triumphs? Who gets to decide? This probe and its message will travel through the galaxy for millions of years, long after Earth has changed beyond recognition. It serves a dual purpose, a scientific instrument pushing the frontier of knowledge, and a cultural artifact carrying the story of humanity to the stars, a true monument to our civilization. Timing and opportunity. Here's the bottom line: if we want to do this, the clock is ticking. The Voyagers completed their grand tour because of a rare planetary alignment. To achieve the incredible speeds needed for this new mission, the Interstellar probe would also rely on a gravity assist from Jupiter. The APL study pinpoints an optimal launch window in the early 2030s. The plan is to launch on a powerful rocket like NASA's Space Launch System and then perform an O-berth maneuver, firing its own engine at its closest approach to Jupiter to get the maximum possible boost. Missing this window could mean delaying the mission for another decade or more, waiting for the planets to once again align for such an efficient trajectory. A mission launching in the 2030s needs to be approved and funded years in advance, meaning crucial decisions must be made in the coming years. This is a generational opportunity, a symbolic passing of the torch to ensure humanity's boldest journey of exploration continues. It requires foresight and a commitment to science that looks beyond immediate returns, a gift to the future. An interstellar probe wouldn't just be repeating the past. It would be a quantum leap forward. It would push deeper, answer fundamental questions about our place in the cosmos, and test the technologies needed for future missions to the stars. The first Voyagers were our first messengers to the galaxy, carrying a hopeful greeting from a small distant world. This new probe could be our new voice, our new eyes, and our first true step beyond the sun's embrace. Are we ready to take that step? Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech. An object from another star system is blazing through our own, and it's putting on a show that has astronomers scrambling. This isn't just another rock, it's an interstellar messenger that's rewriting the rules as it gets closer to our sun, glowing 6 times brighter than anyone predicted. What is fueling this incredible outburst, and what secrets from a distant star does it carry? Let's explore this together. The numbers don't lie. So what do we actually know about this visitor? Let's break down the hard data. Right now, the interstellar comet designated 3I Atlas is roughly 2 astronomical units from the Sun. That's double the distance between the Earth and our star, about 300 million kilometers. Its speed is almost difficult to comprehend. It's currently traveling at nearly 60 kilometers per second and is still accelerating. By the time it makes its closest approach to the Sun, that velocity will peak near 68 kilometers per second. To put that in perspective, that's more than twice the speed of any planet, and fast enough to travel from the Earth to the Moon in a little over an hour. On the brightness scale, 3I Atlas has reached an apparent magnitude of 12. While that's about 250 times too faint for the naked eye, its brightness has been climbing far more rapidly than any models predicted. Its coma, the cloud of gas and dust surrounding the nucleus, has expanded explosively, now rivaling the diameter of Jupiter. While a typical comet nucleus is only a few kilometers across, this expanding atmosphere is what makes it so visible. The sheer scale of this coma is a key reason why it's appearing so much brighter than expected. The unexpected brightness surge. Why is this object causing such a stir? It all comes down to a sudden, dramatic change. In September, 3I Atlas experienced a massive surge in brightness that defied all expectations. The light curve, which is the chart astronomers use to track an object's brightness over time, shot sharply upwards, veering completely off the predicted path. This wasn't a minor increase. The object is now glowing 6 times brighter than models had forecast, a jump of nearly 2 full magnitudes. This jolt sent a wave of excitement and debate through the astronomy community, with experts like Matthew Knight, a specialist in cometary outbursts, analyzing the data. The core of this mystery lies in its coma, the vast cloud of gas and dust that surrounds its nucleus. As the comet gets closer to the sun, its ices are vaporizing at an accelerated rate, causing the coma to swell to an enormous size, now spanning several 100,000 kilometers. This giant cloud is reflecting and scattering more sunlight back towards us, making the entire object appear far brighter in our telescopes. The rapid brightening suggests that highly volatile ices like frozen carbon monoxide or carbon dioxide, which vaporize farther from the sun than water ice, are driving the activity. Racing against the sun's glare. For astronomers on Earth, the clock is ticking. By early October, the window to observe 3I Atlas is closing, and fast. Every evening the comet appears lower in the twilight sky, getting progressively closer to the blinding glare of the sun. The angle between the comet and the sun, what astronomers call solar elongation, will shrink below 30 degrees by October 21st. That's the critical threshold where even the world's most powerful ground-based telescopes, like the Very Large Telescope in Chile, can no longer distinguish the comet's faint glow from the overwhelming brightness of the sky. Amateur astronomy networks are in a frenzy, trying to capture the last possible images before the blackout. Professional observatories, bound by strict safety protocols to protect their sensitive equipment, have already begun to scale back their observations. Pointing a multi-million-dollar telescope too close to the sun is a risk few are willing to take, as it can permanently damage the sensitive optics. This data blackout is happening just as the comet is expected to reach its most active and interesting phase, leaving a huge gap in our understanding. Mars, the last outpost. Just as Earth's view is about to be lost, the observational challenge shifts 225 million kilometers away to Mars. For a short but critical window, the red planet becomes the only outpost with a front-row seat. A fleet of robotic orbiters will become our eyes and ears. The European Space Agency's Mars Express can capture high-resolution images and chemical fingerprints of the coma. The ExoMars Trace Gas Orbiter is designed to sniff out faint traces of gases like water and carbon dioxide, giving us clues to its composition. NASA's MAVEN, led by principal investigator Bruce Jakosky, can use its ultraviolet spectrograph to study emissions from the comet's gas and dust, while the Mars Reconnaissance Orbiter could potentially resolve the nucleus itself with its powerful HiRISE camera, which can see features as small as 1 foot across from an altitude of 300 kilometers. On October 3rd, 3I Atlas will pass within 28 million kilometers of Mars, close enough for detailed study, but far enough to avoid any danger to the spacecraft. This encounter is our last, best chance to gather close-range data before the comet disappears from view. The Green Mystery. One of the most captivating features of 3I Atlas is its stunning green glow. What's causing this otherworldly color? Spectral analysis points directly to a molecule called diatomic carbon, or C2. Here's how it works. As the comet gets pummeled by solar radiation, the sunlight breaks apart larger carbon-rich parent molecules on the surface through a process called photodissociation. This process excites the resulting C2 molecules, and as they relax back to a lower energy state, they release photons of light specifically in the green part of the spectrum, primarily in what are known as the swan bands around 510 nanometers. This phenomenon is seen in many comets, but the intensity of the green hue in 3I Atlas is exceptional. The work of Nobel laureate Gerhard Herzberg, who pioneered the study of molecular spectroscopy, provides the foundation for understanding these emissions. This color is a real-time indicator of how rapidly the comet's surface is changing and shedding material as it barrels towards the sun. The impossible anti-tail. As if a green glow wasn't strange enough, some observers have reported something even more bizarre, a faint feature pointing towards the sun. This is a so-called anti-tail, and it appears to defy the laws of physics. We normally expect a comet's tail to be pushed away from the sun by solar wind and radiation pressure, a phenomenon seen in famous comets like Comet Arend-Roland. However, the unique geometry of this encounter combined with the comet's incredible speed creates a different phenomenon. As 3I Atlas ejects larger dust grains, those particles are less affected by solar pressure and tend to remain in the comet's orbital plane. From Earth's perspective, as we cross that plane, some of this dust can appear to project towards the sun, creating a sunward spike. The late Michael A. Hearn, a leading expert in cometary dust, developed models to explain these complex dynamics, showing how electromagnetic forces can sometimes rival gravity's influence on charged dust particles. While reports of the anti-tail are still tentative, its presence would add another layer of intrigue to this already mysterious visitor. Not like the others. To truly understand how unusual 3I Atlas is, we have to compare it to the only other interstellar visitors we've ever seen. The first, one Oumuamua, discovered in 2017, was a bizarre cigar-shaped object with a high orbital eccentricity of 1.20 and no visible coma or tail. It was a dry, inert shard tumbling through our solar system. 2 years later, 2I Borisov arrived, and it looked much more like a classic comet, with an even higher eccentricity of 3.3. It had a bright coma, a well-defined dust tail, and a chemical makeup similar to comets from our own Oort cloud. 3I Atlas refuses to fit into either of these boxes. Its coma is not only massive but also intensely green, a sign of strong diatomic carbon emission not seen with such intensity in Borisov. Its dramatic brightness surge, a 6-fold increase above predictions, is unlike anything seen with the other two. According to University of Hawaii astronomer Karen Meach, this diversity shows we have much to learn about the small body populations of other star systems. The Mars Encounter Strategy. The hopes of the entire astronomical community now rest on a handful of spacecraft orbiting Mars. Mission planners have spent weeks preparing for the October 3rd flyby, running simulations and allocating precious observation time. The goal is to get a multifaceted snapshot of the comet that would be impossible from Earth. Scientists want to use the high-resolution cameras like MRO's HiRISE, which has a 0.5-meter primary mirror, to try and spot the nucleus and measure its size and shape. Spectrometers will analyze the light from the coma to map the chemical composition of its gas and dust, telling us what kind of alien ices are vaporizing off its surface. Plasma instruments will study the interaction between the comet's atmosphere and the solar wind. No single spacecraft can do it all, and none have promised continuous coverage, but by combining data transmitted through the Deep Space Network, scientists hope to piece together a comprehensive profile of this interstellar visitor. It's a difficult observation, but the potential payoff is a groundbreaking understanding of a body from another star system. Chemistry in motion. Let's dive deeper into the chemistry that makes 3I Atlas so fascinating. The dominant green glow comes from diatomic carbon C2, but it's not the only molecule at play. Some early spectral readings have hinted at the presence of ionized carbon monoxide and the cyanogen radical, both of which can also contribute to a green or blue glow. Debates have already started in scientific forums about the precise mix of these chemicals, often relying on data from powerful spectrographs like the X-Shooter instrument on the VLT, which can cover wavelengths from the ultraviolet to the near-infrared in a single shot. The comet's incredible speed is a key factor here. It means that solar radiation is stripping away fresh, pristine ices from the nucleus at an astonishing rate. We are not just seeing ancient processed material from the surface. We are likely getting a look at the primordial parent molecules that were frozen inside this object when it formed billions of years ago in a completely different planetary system. This makes 3I Atlas a unique chemical laboratory. The fade begins. What happens after 3I Atlas swings around the sun? Its brief moment of glory will be over and the fade will likely begin. Most models predict a sharp drop in brightness as the comet speeds away from the sun's heat, its vibrant coma shrinking and dispersing back into the void. For anyone hoping to catch a final glimpse, it will be a challenge. A large telescope with at least a 20-centimeter mirror will be the absolute minimum, and even then, it will likely appear as just a faint, fuzzy smudge. This is where citizen science will take over. Amateur astronomers and online networks similar to the American Association of Variable Star Observers will pool their observations, using techniques like image stacking to track the comet's retreat. These platforms provide real-time updates on its position and brightness, creating a light curve that professional astronomers will use to understand its behavior. The story doesn't end when it gets dim. Studying the post-perihelion light curve can reveal crucial details about the comet's structural integrity and whether it survived its fiery passage intact. The journey of 3I Atlas through our solar system, though brief, leaves us with more questions than answers. Each data point gathered from this mysterious visitor helps us understand the diversity of objects that wander the galaxy. What does its unique composition tell us about the planetary system where it was born? How many more of these interstellar travelers are out there waiting to be discovered? As it slips back into the darkness, 3I Atlas reminds us that our solar system is not an island, but part of a vast, interconnected cosmos. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Thank you for watching InnoVision Tech. A Harvard scientist just warned the world. Our newest interstellar visitor is shedding metallic alloys that shouldn't exist. Real data confirms a cloud of atomized nickel streaming from the object, but with almost zero iron, a combination that defies natural chemistry. Harvard's own Avi Loeb is sounding the alarm, asking if these aren't natural, what are they? Some whisper it could be engineered. So what is really hurtling through our solar system? Let's explore this together. The discovery of 3I Atlas. Did you know we've only ever confirmed 3 visitors from beyond our solar system? The latest one just rewrote the rules. On July 1, 2025, the Atlas survey team in Chile spotted a faint, fast-moving object. They named it 3I Atlas, signifying it as the 3rd confirmed interstellar object. Right away the math showed this was no ordinary comet. Its path wasn't just a long loop, it was hyperbolic, meaning it was moving too fast for the sun's gravity to ever capture it. This was a one-time visitor from deep space. Astronomers scrambled, finding earlier images of it in data stretching back to mid-June. By the time of its official discovery, it was already inside Jupiter's orbit, blazing toward the sun for a gravitational slingshot that will send it hurtling back into the void. Its incredible speed, roughly 130,000 miles per hour relative to the sun, and its unbound orbit confirmed what the numbers suggested. 3. I Atlas was born around another star and has traveled for an unimaginable time to reach us. Let me explain what makes this more than just a rock. It's a messenger from an unknown star system, and the message it carries is in its chemistry. The nickel mystery. Here's where the story takes a sharp turn into the unknown. Almost as soon as telescopes focused on 3I Atlas, they saw something that shouldn't be there. Data from the Very Large Telescope in Chile revealed a strong spectral line for nickel, a cloud of it vaporizing off the object's core. But what was missing is what has scientists stunned. There was virtually no iron. That's not just unusual, it's unheard of. In every comet, asteroid, and meteorite we have ever studied, nickel and iron are cosmic partners. They are forged together in the hearts of dying stars and locked into the same minerals. You don't find one without the other. Yet 3I Atlas is shedding pure nickel vapor, with iron being conspicuously absent. Harvard astrophysicist Avi Loeb, known for his bold theories, was the first to publicly highlight how bizarre this is. He argues that separating nickel from iron on an industrial scale is difficult on Earth. In nature, it's considered next to impossible. This isn't just a small anomaly. The nickel-to-iron ratio in typical solar system objects is well established. On 3I Atlas, that ratio is completely off the charts. It's a chemical fingerprint that matches nothing we have ever seen. Carbon dioxide dominance. Just when the nickel problem had astronomers baffled, the James Webb Space Telescope added another layer of impossibility. When Webb pointed its powerful infrared instruments at 3Y Atlas, it found that the gas surrounding the object was overwhelmingly dominated by carbon dioxide. The measured ratio of carbon dioxide to water was a staggering 8-to-1, the highest ever recorded for any comet, whether from our solar system or beyond. To put this in perspective, most local comets have a composition where water is the main ingredient, with CO2 making up only a small fraction. Here the roles are completely reversed. This wasn't a fluke, the readings remained consistent over multiple observation sessions. Some scientists propose that this strange chemistry could be the result of a billion-year journey through interstellar space, where cosmic rays cooked the object's surface. But others, including Avi Loeb, wonder if this is another clue pointing toward an unnatural origin. The second interstellar comet ever detected, 2I Borisov, was also considered chemically unusual for its high concentration of carbon monoxide, but 3I Atlas's CO2 levels are in a class of their own. The Oumuamua precedent. This isn't the first time an interstellar visitor has broken all the rules. Back in 2017, the first ever confirmed interstellar object, named Oumuamua, left astronomers scratching their heads. It was traveling at high speed, had a bizarre, highly elongated shape, and most mysteriously, it accelerated away from the sun without any visible reason. Comets accelerate due to outgassing, where melting ice acts like a thruster, but Oumuamua had no visible tail or coma. This is where Harvard's Avi Loeb first entered the public debate. He controversially suggested that the best explanation for Oumuamua's non-gravitational acceleration was that it was an artificial object, perhaps an alien solar sail designed to ride the pressure of starlight. While most of the scientific community proposed natural explanations, like outgassing of hydrogen ice, or its composition as a nitrogen iceberg, none of the theories perfectly fit all the observations. Oumuamua left our solar system before we could get a better look, leaving a legacy of unanswered questions. Its appearance primed the scientific community to expect the unexpected. Now, with 3I Atlas, we have a second data point that defies easy explanation. Ancient sky metal. Humanity's fascination with strange metals from space is nothing new. Long before we knew about asteroids or interstellar comets, ancient civilizations recognized that some iron fell from the sky, and they valued it more than gold. Take the famous dagger of King Tutankhamun, discovered in his tomb in 1925. For decades its origin was a mystery, but modern analysis using X-ray fluorescence revealed its blade contains nearly 11% nickel and a trace of cobalt, a composition that perfectly matches that of iron meteorites. No iron smelted from terrestrial ore in that era had such a high nickel content. This wasn't a one-off. Iron beads found in a 5,000-year-old Egyptian cemetery also showed the high nickel signature of an extraterrestrial origin. The ancient Egyptians even had a name for this material, iron of the sky. These artifacts show us that for millennia, humans have been working with alloys that didn't originate on Earth. They recognize these materials as special, as gifts from the heavens. Now, as we analyze the impossible alloys of 3I Atlas, we're continuing that ancient tradition, questioning the origin of metals that fall from the sky. Kilonova formation theory. So, if the metals on 3I Atlas are natural, how could they have formed? There are a couple of cosmic forges violent enough to potentially create such exotic materials. The first is a kilonova, the cataclysmic explosion that occurs when two neutron stars collide. These events are among the most powerful in the universe, and for a few brief seconds they create conditions perfect for the R process. A rapid-fire sequence of neutron captures that forges elements heavier than iron. In the chaos of a kilonova, the normal rules of element production can be broken. Some theoretical models predict that the debris cloud from such a merger wouldn't be uniform. Instead, it could contain pockets of matter with strange elemental imbalances, regions that are incredibly rich in elements like nickel, but poor in iron. If 3I Atlas condensed from one of these exotic debris patches millions of years ago, it would carry a chemical signature unlike anything from a standard supernova or our own solar system's formation. This theory provides a potential natural explanation, but it relies on an event that is both incredibly rare and violent. Asymmetric supernova theory. There's another, equally extreme possibility, a lopsided supernova. We tend to think of supernova explosions as perfectly spherical blasts, but, well, that's not always the case. Some massive stars die in these chaotic asymmetric explosions, flinging different elements in different directions. Astronomers have actually seen this in action by studying supernova remnants like W49b. X-ray observations from NASA's Chandra Observatory show that in W49b, iron is concentrated near the core of the remnant, while other elements were ejected outward in high-speed jets. This proves that nature really does have a mechanism for separating elements during a star's death. If a star's core collapses unevenly, the resulting explosion can be directional, creating plumes that carry specific elements hundreds of light-years away. So, it's plausible that 3I Atlas could be a fragment formed from a jet of nearly pure nickel, blasted away from its parent star while most of the iron stayed trapped near the core. Like the kilonova theory, this is a natural explanation. However, it requires a very specific and honestly, pretty violent type of stellar explosion to create the chemical signature we're seeing. Statistical improbability. Beyond its strange chemistry, there's another red flag that has Avi Loeb and others asking serious questions: the object's trajectory. According to Loeb, the probability of a random interstellar object passing so close to several planets in our solar system, Venus, Mars, and Jupiter, in a single flyby, is astronomically low. His calculations put the odds at about 1 in 20,000, or 0.005%. For an event this rare to happen with only the third interstellar object we've ever detected is, to him, statistically suspect. Furthermore, the object's path is nearly aligned with the plane of our solar system, but it's moving in the opposite direction of the planets. This retrograde orbit allows it to sweep past the inner worlds in a way that looks almost like a survey mission. To add to the suspicion, 3I Atlas reaches its closest point to the Sun on the far side from Earth, making it incredibly difficult for us to observe when it's most active. Critics argue that in a vast universe, rare events are bound to happen. But Loeb counters that when multiple anomalies, the metals, the chemistry, and the trajectory, all point in the same strange direction, the possibility of an artificial origin must be taken seriously. The Golden Record Parallel. In 1977, NASA launched the Voyager 1 and 2 spacecraft, each carrying a golden record. This was a project led by a team chaired by Carl Sagan, intended as a message in a bottle cast into the cosmic ocean. The records contain sounds, music, and images portraying the diversity of life and culture on Earth, designed for any intelligent extraterrestrial life that might one day find them. Sagan famously said the act of launching this bottle says something very hopeful about life on this planet. The Golden Record is a time capsule, a physical object carrying information across vast distances and times. Now consider 3I Atlas. It's an object carrying materials with a chemical composition so strange it looks like a deliberate signal. This has led some to draw a parallel. What if 3I Atlas is its own kind of golden record? Instead of a message encoded in grooves on a disk, perhaps the message is written in the very atoms of the object, in the unnatural ratio of its elements. It's a sobering thought. We sent a message out into the void, trusting that matter could carry meaning. What if someone else had the same idea? Atomic messages. If 3I Atlas is a message, how could it be written? The answer might lie in isotopic encoding. Isotopes are versions of an element with different numbers of neutrons. On Earth, scientists can already store information at the molecular level by creating unique isotopic fingerprints. By precisely controlling the ratios of different isotopes in a material, you can create a pattern, a kind of atomic QR code that would never occur in nature. An advanced civilization could theoretically bake a message into a metallic object, making it durable enough to survive a journey of millions of years through interstellar space. Such a message would be immune to the cosmic noise that can degrade radio signals. The information would be in the fine print of the object's chemistry. This is why every scrap of data from 3I Atlas is being scoured for these hidden patterns. Are the isotope ratios what we'd expect from a kilonova, or do they show a level of order that points to intelligent design? We're not just looking for a rock anymore, we're looking for a signal hidden in matter itself, a message that has waited eons to be read. Right now we stand at a crossroads. Is 3I Atlas a product of nature at its most extreme and exotic, formed in the heart of a cosmic catastrophe we can barely imagine? Or are we looking at something else entirely, a piece of technology, a messenger, or a calling card from a civilization beyond our own? The data from the Very Large Telescope and the James Webb Space Telescope has broken our existing models and forced us to confront possibilities once relegated to science fiction. The search for answers is just beginning, and the next discovery could change everything we know about our place in the universe. Don't forget to like, subscribe, and hit the bell icon for more deep dives into cosmic mysteries. Thanks for watching InnoVision Tech.